First of all, I'd like to thank the organisers and thank Przemek for inviting me here to be able to give a talk. My name is Marek Szablewski, and contrary to what happens in undergraduate lectures which I give back in Durham, I don't have to spend 5 minutes explaining how to pronounce my name, here at least. Right, so I'm going to talk a little bit about some DADQs. My presentation will talk a little bit about the materials, a little bit about some characterization, a little bit about some spectroscopy, and possibly at the end some applications. The picture here of the cathedral in snow is just to prove it does snow in England occasionally, but you have to get up very early in the morning to take a picture like that because it doesn't last very long unless you live somewhere out in the sticks like Andy does. So, my favourite molecule, TCNQ. The story this morning about portholes from submarines being used as windows in electric spectroscopic cells reminds me of sort of consequences of maybe unintended reasons why things happen. It's often said that one of the byproducts of the race to go to the moon was the discovery or the implementation of Teflon as a non-stick surface for frying pans. Well, TCNQ is a sort of byproduct of that because the people at DuPont who first synthesized TCNQ were actually, when TCNE as well, were actually trying to make polytetracyanoethylene rather than the fluoro version of the polymer. Unsuccessfully, I might add, but we ended up with a TCNQ molecule, which, as one of my PhD students told me, says at least you could have made a career out of it. So TCNQ is a very strong electron acceptor. It's got a high electron affinity of about 2.8 EVs. It's an organic material. It's extremely planar, as you can see from the mugshot here. And it very easily forms radical anion salts, which is sometimes a blessing and sometimes a problem. So this is one of the first reactions of TCNQ, which was reported back in the 1960s, where we have a sort of a substitution of first one nitrile group with a primary or a secondary amine, and then replacement of a second one with another amine or the same amine to give us a di-substituted TCNQ. The reaction is always 1,6. It always occurs at the same end of the molecule. And it seems from that reaction scheme that this is extremely simple and straightforward, and it can be, but it can also be very complicated. It's a nightmare to try and work up some of the side things that happen. And actually this reaction here, which results in what is a purple material, is something that we're probing now. One of my students is looking at, and it would seem that the purple material we get as the intermediate is not actually what everybody's thought it's been since the 1960s, but there'll be more on that at a later date, I hope. So you can control what you put on here. You can tune the amines you put on the end here, and you have a range of compounds which are very yellow. There's a single peak, depending on what you've put on the end here and depending on what the solvent is, about 400 nanometers in acetonitrile. You can see it's a nice clean peak. There have been some kinetic studies carried out on this reaction, but again, they may now be somewhat problematic. So we discovered more pips. So this is a version of this material which has a morpholine on one nitrile and has a piperidine on the other. We discovered by accident many years ago that it fluoresced very strongly in the solid state. So basically the student allowed the sample to evaporate away, and we ended up with these microcrystals, and you can see them here under a UV lamp. They fluoresce very nicely. So how does this manifest itself? Well, we've got two spectroscopic cells here filled with glycerol solutions of one of these fluorescent adducts, these TCNQ adducts. One in glycerol, one in methanol. They look pretty much the same when you look at them under normal daylight, but if you look at them under UV, you can see there's a dramatic difference in the fluorescence you see. So in the glycerol, you've got a very nice strong emission. In the methanol, there is an emission, but it's incredibly, incredibly weak. So for this particular talk, I'm going to talk about this series of materials. You can see they're all related. So the simple one, the diamino, is simply replacing them with two amine moieties, a little bit more complex. We've replaced one with a morpholine, gives us a bit more solubility. And thirdly, we have the morpip, which is the morpholine and the piperidine adduct there. So they get bulkier as we go through the series. There should be different interactions with the environment. So as we saw, the fluorescence that we saw there is extremely environmentally sensitive. We can see here, these are emission spectra of morpip in a range of different alcoholic solvents. From the least intense spectra down here are things like methanol, ethanol, propanol, butanol, pentanol, hexanol. This one here is diethylene glycol, and this one is glycerol, which is the quantum yield increases hugely as the rigidity of the matrix in which it is increases. You could say that it was the I've forgotten the word here now. It could say that this was due to the viscosity. Thank you very much. The viscosity, but not only, because if you put it into a polymer film, you have the same effect. So if you put it into, or if you freeze it, you also have the same effect. So viscosity is one way of describing that. And on the second part of this slide, you can see the absorbance spectra in black, the excitation of the green dashed lines, and the fluorescence, which is the blue solid lines, of each of those three compounds. And you can see there's these are all in ethanol, but you can see there's a shift between the absorption spectra of those different molecules, whereas the fluorescence spectra are all pretty much similar. So we did a little bit of work on trying to look at the Stokes shifts as a function of reaction field of a range of these molecules. In fact, this is another similar material that we looked at, and you can see that when you look at when you use the Lippert's equation to calculate the reaction field here, you can see we have essentially linear responses apart from the very viscous alcohols, so the diethylene glycol, the glycerol, and the ones at the end of that scale. They don't fit the model. So a better fit is using by an ET30 scale, which includes, which takes care of solvent-solute interactions such as hydrogen bonding, and you can see that's a very nice linear responses that we get in terms of that scale when related to the Stokes shift of this material. So as I said before, in glassy media, we have a very similar response. So when you put them into a glass-forming solvent such as 2-methyl tetrahydrofuran, we have an increase in the quantum yield from 0.4 at room temperature in one propanol to about 13%, just below 200 K. And in a PMA matrix, so just a guest host film which is spun, we have an increase on is only about 2 to 3 times. However, the quantum yield is about 20% increased. And we have an example. We were looking at this in ethanol, and you can actually you can determine very nicely the freezing point of ethanol if you put this in a cryostat and look at the fluorescence as it's emitted. So we also looked at some solvatochromism. So we looked at the absorption spectra of these chromophores in various solvents, and unsurprisingly, we found that these molecules had displayed a negative solvatochromism. They have a negative beta second order hyperpolarizability, and initially we were looking at these in terms of nonlinear optical applications, but then moved on to look at the luminescence properties. So the Stokes shift is almost identical in its dependence to the absorption, and this implies that the excited state dipole moment is approximately 0, and we'll come back to that later because that has consequences. There is no solvent dependence of the energy of the emission maximum, so that would indicate that this statement could be true. And preliminary and some theoretical modelling implies that the excited state is approximately planar, so it's flat. So here we have some ab initio calculations for the ground state, and we get a dipole moment of about 15 dBs, and experimentally for these materials we get dipole moments of between 15 and 20 dBs, depending on what we have on the end, on the acceptor and on the donor end of the material. And that's the conclusion is that it's related to some sort of a twist, and you see this in the crystal structure. And if you model the twist angle here, you can see that you get to a point where you have the conformation changes are costing less in energy than an increase in the ground state dipole moment. So we have a ground state dipole moment which is approximately 0, and a ground state dipole moment which is about 15 to 20 dBs, and an excited state dipole moment which is approximately 0, or very slightly only positive. And this is an optimized geometry of the diamino material, and you can see that there's a twist here between the flat TC&Q part of the molecule and the bit on the end here with the two amine moieties. So this is holding up very nicely so far. So these are some calculations of the HOMO and the LUMO on that same molecule, the diamino molecule, and you can see that the HOMO is sitting mostly on the dicyanomethanide part of the molecule, and it's quite closely bound into that, whereas the LUMO is more smeared over the two amine ends of the molecule up there. As we said, there's a problem with charge transfer and DFT, but there is some meeting of the two in the ring system here, where you have about 40% of the LUMO, 40% of the LUMO and about 30% of the HOMO are overlapping in the ring structure. So here are some time-resolved fluorescence spectra of the three molecules in ethanol, and from this you can conclude quite a lot, coupled with the other information that we've got. So one is, if you remember, one is the simple one with the two amines. Two is got one amine and the morpholine, and three is the one with the two rings, the morpholine and the piperidine. So the decay process of the excited state is very fast, and it's a non-radiative process, and it's dominated by these intramolecular twists. It's on a picosecond time scale, and it's very dependent on the medium in which you're observing it. We did at one point think that hydrogen bonding was going to be very crucial in this. Now, obviously, hydrogen bonding is giving us our viscosity, it's giving our dense three-dimensional structure, particularly in something like glycerol. But there's an interesting adduct to that, is that when you've excited the molecule, it's got 0 dipole moment and it's fairly planar. It's essentially interacting with nothing. It's fairly chemically inert, and that's quite unusual for an excited state. So it's not actually interacting with hydrogen bonds, so it's not making and breaking hydrogen bonds as it changes. Now, there may be implications in terms of solvation and packing of solvent molecules around the excited state and when it decays back, but the hydrogen bonding isn't the reason, because otherwise what you observe here is that the leading factor is the steric hindrance, the large size of the groups which changes the decay process, and the medium in which you're actually observing it. This is which is a fairly weak emission. We had to work with quite dilute solutions to make sure we weren't getting any sort of aggregate. So it's about 10 to the minus 6 molar solutions we were looking at for these decays. So the hydrogen bonding would give us a deviation from the linearity, which we would expect that, but we don't see that. We only see the effects essentially of friction in terms of steric hindrance and matrix. So this is the plot of viscosity against the rate constants for the fluorescence, which are plotted against the inverse of the viscosity in this case for ethanol, pentanol, octanol and decanol. And you can see that there are nice linear responses which you wouldn't have seen if hydrogen bonding would have been the prevalent mechanism. So this is another technique which is rarely used for anything practical. It's a sort of answer, but what's the problem? The Langmuir-Blodgett technique. But it does sort of remind me of the mention yesterday of the zone casting technique, where you're getting things to align because of the way they flow out of a nozzle. So we can arrange molecules theoretically on using a blodgett trough on an air-water surface if we've put some sort of a hydrophobic chain, an aliphatic chain onto these molecules. And then we can build up multi-layers, and we can look at the fluorescence spectra. So this was the setup we used. And we can actually perturb the films. So we actually were putting things onto the films to see if we could change the environment in which the films found. Now the films are already in a quite ordered situation, so it's not really like they are in the solution. They're quite, it's almost a solid monolayer. So we're putting a drop of polymer on there, or human serum albumin, which is a protein, in water, adding that to films, and then looking at how that affects the fluorescence. And we were comparing the lifetimes and the spectra. So that's a photograph of not the world's best film, but it's a photograph of an LB film under UV light. You can see the blue emission there very clearly, and you can also see there are more layers here than there are here than there are here. So this is the number of dips here is higher than it is here or here, but you can see it's quite an intense colour. There are lots of striations and streaks. We found a way to combat that now. So instead of using a traditional LB technique where you use a syringe to deposit onto the surface, we now aspirate with a sort of well, the first version of this was a sort of a perfume aspirator, a spray that we could spray onto the surface. You get a beautiful, undisturbed and striation-free monolayer on the water surface. And here are the spectra, the fluorescence spectra of our monolayers. Remember, we're dealing with very small quantities here, 2 layers up to 12 layers. And there's a bit of a jump here between 10 and 12. They're not in the right order. Perhaps we have areas of the film which are not covered as well as others. So it's in its infancy really, and it's not by no means perfect as a technique to build up layered systems. But you can see that there is here some data here that shows that the unperturbed films, so the films with nothing on them, are the blue squares here, repeated on a number of occasions. And you can see with PMMA we have some increase in the average lifetimes, but with the human serum albumin even more so. So there is some effect there in terms of adding something onto the surface which is interacting with the exposed ends of the molecules. And this is what we think is happening in the organization that we have. It's an interaction actually with the hydrocarbon chains, where we think which would be on the surface if it's deposited in the way we expect it to have deposited. Again, reducing some of that rotation, some of those non-radiative processes, giving us the fluorescence that we would expect, and enhancing it even because of its interfering even more. So that's almost it. I would just say that we're also using the LB film, LB trough, to do something slightly strange. We're also doing, we've taken graphene, we've exfoliated graphene, and then we're trying to reassemble graphene as multi-layers using an LB film. So we actually have some multi-graphene layers that we can actually try and do some experiments and possibly having putting other monolayer materials in there, such as molybdenum disulfide in between the graphene layers. So LB is finding some usefulness, even though it's a technique which is much derided and little used. Thank you very much.
Very interesting talk. Time for questions.